The principle of mathematical induction is a method of proof that is often used to quickly show that an observed pattern must continue to hold ad infinitum. Now, before we get into the nitty-gritty of some examples, let's get our heads around how the principle of mathematical induction can be invoked and what it implies. To that end, consider the following metaphor: dominoes. Now, I'm willing to bet that most folks out there have played with dominoes before. Maybe not the actual game associated with them, but most folks at some point in their lives have probably set them up in a row like this, and then by simply knocking a single domino over, started a chain reaction in which all of the dominoes fell. This is the core idea behind mathematical induction. Let's think about this carefully. In order for you to be assured that all of the dominoes would fall, what did you need to do? Of course, everyone answers, push over the first domino, and this is true. But there's something else that we need to do as well, something that we need to do even before pushing over that first domino. Consider this row of dominoes. If I push this first one, will they all fall over? Well, of course not. There's this big gap in the middle. These dominoes were not set up correctly. You see, for me to be confident that all of the dominoes will fall, I need to assure myself that the dominoes are spaced appropriately. I need to assure myself that if the first one falls, then the second one will fall. And if the second one will fall, then the third one will fall. And if the third one falls, then the fourth one will fall, and so on. To speak more generally, I need to assure myself that if the kth domino falls, then the k plus 1th domino must fall as well, no matter what k might be, whether it be the first or the second or the third or the 6th or the 100th and third, whatever. So to be assured that all of the dominoes will fall, I need to assure myself of two things: that the first domino falls, and that if the kth domino falls, then the k plus 1th domino will fall, regardless of the value of k. Now, what does this have to do with mathematical proof? Suppose you are looking at sums of the first n positive integers. So if n is 4, you're looking at 1 plus 2 plus 3 plus 4. If n is 5, you're looking at the sum all the way up to 5. And of course, the sums are listed over here. And you discover something very interesting. There's a way to rewrite these numbers so that a certain pattern emerges. Namely, we could write these values like this, where, for example, this guy right here, the 6, the sum of the numbers from 1 through 3 is obtained by starting with 3, multiplying it by the number that is 1 greater than that, and dividing by 2. For the sum of 1 through 4, again, we start with 4, we multiply by the number 1 greater than that, and we divide by 2. And that seems to work out here for the first several rows. It seems that the sum of the first n positive integers is always taking the form n times n plus 1 over 2. Now, having checked this for several values of n, we have some good empirical evidence that this might be true, but that's not proof by any stretch of the imagination. Indeed, we can check to see if this statement is true for as many values of n as we wish, but since there are infinitely many possibilities for n, we can never verify the statement for all of them. We enter the principle of mathematical induction. I want you to take each one of these statements, where n is 1 or 2 or 3 or 4, shown here in blue, and think of them as dominoes. So this statement here, the statement when you replace n with 1, that's our first domino. This statement here, when you take this guy and replace n with 2, that's our second domino. And this statement here, when you replace this n with 3, that's our third domino, and so on. Okay? Now, I want you to equate in your mind the various blue statements here being true with the corresponding dominoes falling. We, of course, would like to show that this green equation here is true for any positive integer n. We would like to equivalently show that every single one of these blue statements is true out to infinity. Equivalently, we would like every single one of our dominoes to fall. Now we know how to get all of our dominoes to fall. All we need to do is knock over the first domino and make sure that if the kth domino falls, then the k plus 1th domino has to fall, regardless of what k actually is. So this has to work when k is 1, when k is 2, when k is 3, and so on. Okay, what does that mean in terms of our statement? All right, we need to show that the first statement is true. The statement here when n is 1. This guy. That's easy enough to verify. We can check the arithmetic on that. Then we need to look at this statement when n is k. We're looking at the kth domino here. This guy right here. If that's true, if this domino falls, we need to be assured that this domino will fall. If this statement is true, regardless of what k might be, we need to be assured this statement is true. Okay, so let's recap what we have so far. First, we have a statement that we're trying to prove for all values of n, or at least all positive integers n. For us, that statement is this one, that the sum of the numbers 1 plus 2 plus 3 all the way up to plus n is equal to n times n plus 1 over 2. That's our statement. It's either true or false for any given value of n. We hope to prove that it's true for every positive integer n. So to prove this, with mathematical induction, we'll need to do two things. The first thing we'll need to do is to ensure the first domino fell. We need to make sure that this statement makes sense, that it is true when n equals 1, the smallest value of n I want to consider. Of course, looking at this thing, if we look at the left-hand side, right, the left-hand side when n equals 1, what do we have? We've got a 1, that's what our sum starts off with, plus a bunch of stuff all the way to n. Of course, n is 1, so it looks like that's all we have. Okay, so we know the value on the left-hand side. What about the value on the right-hand side? Well, that's easy. If n is equal to 1, we can just plug that in. So this is 1 times 1 plus 1 are 2 over 2, and of course the 2's cancel, and we get 1. And looking there, 1 equals 1. Yay! This statement is true when n equals 1. The first domino just fell. Okay, but that's not all we have to do. We need to assure ourselves that if this statement is true when n is k, regardless of what k is, then it's going to be true as well when n equals k plus 1. Okay, so we'll start off supposing that it is indeed true when n equals k. Okay, so here we go. If 1 plus 2 plus 3 plus ... all the way up to k equals k times k plus 1 over 2, regardless of the value of k, if this is true, then can we argue that 1 plus 2 plus 3 plus ... plus k, and go right past k to k plus 1, can we argue, put a big question mark there, that that should be k plus 1 times k plus 1 plus 1, or k plus 2 over 2. Okay, can I get from here to here? Look, I'm trying to show an equality here. This is kind of like proving trigonometric identities, if you're familiar with that. The strategy, of course, should be to pick one side here and massage it, play with it a little bit, play with its form, tweak it here, there, and a little bit, until we can get the left-hand side to look like the right-hand side. Okay? I don't expect to be able to jump straight from here to here in one step, but hopefully I can say, well, this equals something, and that something equals something else, and that something else equals yet another thing, and this yet another thing actually is this. Okay? Then I'll have shown this is true. But understand, I'm working under an assumption here. I need to use this piece of information somewhere in establishing this. Okay? If I could establish this without using this little piece, I probably wouldn't need a proof by induction anyways. So I need to use this piece of information. This piece of information, this supposition, is so important we even give it a name. It's called the inductive hypothesis. Okay? So now how am I going to use this? Well, this is a statement about equality. If I see this, it's equal to this. If I see this, I could replace it with this. Okay? One way I can use this piece of information is via substitution. So I need to be on the lookout for that. 1 plus 2 plus 3 plus ... plus k. If I can see that down here somewhere, then I could replace it with this, and I will have used the inductive hypothesis. Okay? If I don't see it right away, I want to play with the expressions I'm given down here until I can see it, until I can have an opportunity to use this. But looking here, it's rather quick, isn't it? Right there he is. That's the sum from 1 all the way through k, and then just with another term tacked on here. So I could replace all of this stuff, 1 through k, with this. Now what does that give me? Well, I've got k times k plus 1 over 2. Again, I'm just replacing that with that, plus this extra term. So now the question isn't, is this equal to this? But can I get this equal to this? Well, let's look at the form here. We have a fraction plus something else here. Here we have a single fraction. Maybe we should collect these together into a single fraction, get common denominators and all that. So wouldn't we have a common denominator of just 2? So here we need to multiply top and bottom here by 2. So plus 2 times k plus 1. And then over the common 2. But now look, there's a common k plus 1 on both of these terms. I could factor that out. Now what does that leave? We have a k here. We have a 2 here. That's all over 2. Looky there. It's the same thing. This really does have to equal that if this is true. Check. So, going back to here, if n equals 1, the smallest case of n that we want to consider, our statement holds. Our first domino fell. And 2, if this statement is true when n is k, then we can argue, using that piece of information, that this statement must also be true when n is k plus 1. Okay, so if the kth domino falls, the k plus 1th domino has to also fall. Taken together, all of the dominoes fall. Taken together, this green statement is true for all values of n. Okay, so we write something equivalent to that, formally acknowledging that we're using the principle of mathematical induction. These are the two elements, of course, that are required to use the principle of mathematical induction. And then what the final result is, and clarifying very specifically which values of n this makes sense for as a result of the induction argument. Okay, 2 more quick things here before we wrap up. This first step here where you're checking to see if that first domino falls or if the statement you're talking about is true for the smallest value of n you wish to consider, this is called the basis step. Okay, and this piece over here where you're checking to see if the kth domino falls, then the k plus 1th domino must fall. If this statement is true when n equals k, then this statement must be true when n equals k plus 1. This is called the inductive step. Okay, so those are the 2 pieces you need to be able to invoke the principle of mathematical induction. That's it. I suppose we should end with some slightly more formal statement of the principle of mathematical induction, although its essence, again, is captured in this idea of dominoes. But here is one possibility. If S of n is some statement regarding a positive integer n, so this might be a statement about sums of integers, it might be a statement that's an inequality, it might be a statement involving something entirely different, like how many moves it takes to solve a particular puzzle or something like that. Okay, but it's some sort of statement that depends on the value of n. So as you change n, you get different statements, those statements in blue that we saw before, one per domino. And S of 1 is true. Okay, this establishes your basis step. The first domino has fallen. And if S of k is true, so the statement's true when n equals k, then the statement must also be true when n equals k plus 1, or S of k plus 1 is true. So this is the inductive step. Those things taken together with the principle of mathematical induction will lead you to the conclusion that your statement, S of n, is true for all of these values of n equals 1, 2, 3, dot, dot, dot. Now I'll make one note about this. This one starts off at 1. That frequently happens when you're looking at induction arguments, but it doesn't have to. We could start at any domino we wish, understanding, though, that only the dominoes after that will fall. So if we change this to S of 5, then this is only going to be true for n equals 5, 6, 7, and so on. If we make this 7, then it'll be 7, 8, 9, and so on. Okay? So one little possible change there. All right? That's it. Hopefully you have a little bit better understanding of the principle of mathematical induction now.